Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afzal bin Nordin, student ID 20524 from group 39. So today we would like to present about the collapse of the Tacoma Narrows Bridge for Engineers in Society group project. So this is all our team members, consists of 5 students from uh, 3 different courses. So first and foremost, we like to present about the project background. So for the Tacoma Narrows Bridge, it was built in 1940 and was known as the Suspension Bridge in Washington, USA. In terms of this design and construction, it is known for its lightweight and narrow design, which makes it susceptible to wind forces. The collapse event occurred on November 7, 1914, due to strong winds, which has caused the extreme oscillation and lead to the failure. The main cause for this event, based on our studies, is due to aeroelastic flutter, where the wind induced vibration and has amplified the bridge movement. So the impact and lesson from this event has led to a major advancement in bridge and engineering standards. Next, there are 3 objectives from this project. The first one, bridge collapse investigation. So we would like to identify the causes, safety issues, and ethical concerns. The second one, we would like to assess the impact on engineering standards, where we assess the effects on safety regulations and also in terms of the bridge design. And the last one, future prevention, where we would like to recommend the better engineering practices and ethical decisions.
We move into the key technical issues that led to the collapse of the Tacoma Narrows Bridge in 1940. First, structural design flaws. The bridge used 10 8-foot plate girders instead of 25-foot trusses, making it highly flexible. This caused excessive movement even in light winds, earning it the nickname "galloping gertie". Next, aerodynamic instability. The solid plate girders trap wind, leading to vortex shedding and resonance. Eventually, a phenomenon called torsional flutter caused the bridge to twist violently at 45-degree angle before collapsing. And finally, material and construction issues. The lightweight steel structure lacks stiffness, and attempts to fix oscillations like tie-down cables and hydraulic dampers are failed. More importantly, no wind tunnel testing was done before construction, a critical oversight for this problem. In conclusion, the Tacoma Narrows Bridge failed due to poor design, lack of aerodynamic consideration, and weak materials. This disaster changed engineering forever, making wind testing a standard for all modern bridges.
Next, for the ethical reasons, there are 3 ethical reasons for this incident. The first one is insufficient testing, which a failure to identify torsional flutter, a hazardous twisting motion brought by the wind. The second one is ignoring early warning. Although the bridge is unusually bouncing, nothing was done about it. And the last one is cost savings. The project used minimum stiffening materials that prioritize cost savings over safety.
Assalamu alaikum. Next on the agenda is the recommendations. Let's begin with structure design considerations. The first one is increased stiffness and rigidity. Using stiff girders, cross bracing will enhance rigidity and stability. We move on to damping mechanisms. Adding tuned mass dampers, shock absorbers, and aerodynamic dampers will control vibrations and improve safety. The last one under structure design consideration is the reinforcement of anchorages and cables, and this can be done using multiple parallel cables, which will distribute load efficiently and increase stability. Moving on to the aerodynamic considerations. The first one is the streamlined deck design. Open truss designs and aerodynamic shaping will reduce wind forces and vortex formation. We move on to wind tunnel testing and CFD. This one, comprehensive testing and simulations will optimize aerodynamic stability. Lastly but not least, under aerodynamic consideration is vortex shedding control. Installing fairings and stabilizers will suppress these vibrations and improve wind resistance. On the recommendations, is the ethical engineering practices that we should adhere to in order to avoid such a tragedy from happening again. There is accountability and responsibility, informed consent and public safety, environmental and social responsibility as well. In terms of risk assessment and management, we first have to do comprehensive risk identification and analysis. And after identifying the risks, we go and do risk mitigation, which is to avoid the risks above.
So for the conclusion part, we're divided into 5 sections. So the first one is the key lesson. So the key lesson we learned from the Tacoma bridge collapse is that innovation must be balanced with rigorous testing and safety measures. Next is the technical failures. The collapse of the Tacoma bridge was mainly due to design choices, which was due with the slender and the flexible griders, which led to the catastrophic aeroelastic flutter, which thus led to the collapse of the bridge. Next is the ethical considerations. So safety should never be compromised for cost savings, and early warning signs must be taken seriously and addressed promptly. Next is the legacy and impact. The collapse of the Tacoma Bridge transformed modern bridge design standards, which thus improved the resilience of modern bridges. So for the final takeaway, the collapse of the Tacoma Narrow Bridge remains a powerful reminder of the critical interplay between innovative design, ethical responsibility, and public safety. That is all from Group 39 for EIS. Thank you.